Hello, everybody. Welcome back. We are about to start the last half of section 4.2. We left off in the middle of problem 1 doing the second derivative test on various functions. Now, the second derivative test is a way that we can find any local maximums and minimums, but it's a different way than what we learned early on in chapter 3. So we're going to continue on and do problems D, E, and F while we're still doing the second derivative test. We're going to dive right on in here. If we have my function here is x squared minus 32 square root of x plus 1, and it tells me to find any local extrema using the second derivative test, then the first thing that you need to do is find any critical numbers. Because those critical numbers are going to be my maximum and minimum candidates. And fortunately for us, when I'm talking about finding local extrema, actual maximums and minimums will only occur in values where your derivative is set equal to 0. So what I'm going to do is take this function and find its derivative. And once I find its derivative, I'm going to set it equal to 0. So before I start taking the derivative, let's rewrite my original function to look like x squared minus 32x to the 1/2. So instead of square root of x, I see x to the 1/2 there. That's because I'm getting ready to take the derivative, and I want to use a power rule on that. So let's take the derivative of f. The derivative of x squared is 2x. Derivative of negative 32x to the 1/2, we're going to do a power rule. Negative 32 times 1/2 is minus 16. X to the 1/2 minus 1 power is negative 1/2. And the derivative of 1 is 0. So this is my derivative function, and it would be best for us to make this proper by taking this x to the negative 1/2 and popping it down into the denominator. So this looks like 16 over x to the positive 1/2. Why do I do that? Because I'm about ready to do algebra with this. I'm about ready to set this equal to 0. So if I'm getting ready to do algebra, solving for x style, then it's best to have all of your exponents where they go. So if you have a negative exponent, make it positive by putting it in the denominator. I have 2x minus 16 over x to the 1/2, and this is set equal to 0. So I'm going to solve this algebraically. There's a couple of different routes you can take, but what I'm going to do is I'm going to take this term over here and add it to this side. So that I get 2x is equal to 16 over x to the 1/2. Now what I'm going to do is try to get this x to the 1/2 out from the denominator by multiplying both sides by x to the 1/2. That means it'll cancel on this side, leaving me with 16 over here on the right. And on the left, I've got to figure out what x times x to the 1/2 is. Now, laws of exponents say that exponents add here. This is x to the 1 plus 1/2 power. So you have x to the 1 plus 1/2, it's 3/2. 1 plus 1/2 is 3/2. So we have 2x to the 3/2 here equals 16. Let's divide both sides by 2 now to get the x to the 3/2 by itself. And you have x to 3/2 is equal to 8. I'm really close to solving for x. Here, it might be beneficial visually to now transform this power into its root equivalent, just so I'm a little more comfortable with how this is going to work. This will be the square root of x cubed, if I transform that back into a root. So if I'm going to get x by itself, the next thing I'm going to do is square both sides so that it gets rid of the square root. I'm then left with x cubed equals 64. And then I cube root both sides since that's x cubed. And if you cube root 64, you get x is 4. Since this is a cube root, you do not have to do plus or minus. Odd roots do not have the plus or minus case when you take a root. So I have one critical number, and it's x equal 4. Now, what we do as part of the second derivative test, once you have your critical number, your maximum candidate, you're going to plug the critical number itself into the second derivative. Second derivative. So if you don't have the second derivative function already, then you need to find it. This is my first derivative. Here it is. Take the derivative of it before we simplified it back. We have f double prime, the second derivative. The derivative of 2x is 2. Then I have a power rule here. Negative 16 times negative a half. 16 times a half is 8, and a negative times a negative is a positive. So I get plus 8x to the negative 1/2 minus 1. Negative 1/2 minus 1 is negative 3/2. So this is my second derivative. And here is where it might be comfortable if we take this x to the minus 3/2 and flip it back down now that I'm done taking the derivative again. This is my second derivative function, f double prime. You're going to take 4 now, your critical number, and plug that into the second derivative. I get 2 plus 8 divided by 4 to the 3/2 power. Now, I'm supposed to punch this out, but given that all of these values are positive, 2 plus 8 divided by 4 to 3/2, I anticipate I will get a positive result here. And if you get a positive result from the second derivative, right, I plugged in my critical number, I got a positive result from the second derivative. So that tells me, and all that this tells me, is that f is concave up, right there at x equal 4. Positive value for the second derivative means concavity is upward. And now I'm supposed to draw an additional connection here. If 4 is my critical number and it's potentially a max or a min, and I found out that my function is concave up, we have to put 2 and 2 together. If that's a max or a min and it's concave upward, which one does it have to be? It has to be a minimum. So we would have to say that there is a min at x equal 4 due to this shape. In order to finish this thing up, you will need to find the point xy for this minimum. So we have the x value is 4, and if I'm going to find the corresponding y value, you've got to take 4 and plug it back into the original function. Remember, the original function cranks out y values. That's what it's for. And if you take x equal 4 and plug it back into the original function up here, you would get a y value of negative 47. So what we would say is that there's a local minimum at x equal 4, and the local minimum is negative 47. And then we are done with this problem. Let's scooch on down here to the next one. Same directions. Find any local maxes and mins of this thing by using the second derivative test. What that means is I'm going to need to find the critical numbers and plug them into the second derivative. So first step is find your critical numbers, because those are my potential maxes and mins. To find critical numbers, we are going to take the derivative and set it equal to 0. That means my original function, I need to make it look more derivative friendly. Take that square root and write it as its equivalent 1/2 power. And now I'm going to take the derivative of this. Since this is something in parentheses to a power, you will need to use a general power rule to take the derivative. So let's do it. C times R, 1 times 1/2 is 1/2. Leave the inside alone. Decrease the power by 1. So 1/2 minus 1 is negative 1/2. This is the power rule. C times R, x to the R minus 1. But as part of the general power rule, remember, you have to multiply by the derivative of the inside function. The derivative of x squared plus 25 is 2x. Now, what am I getting ready to do with this? If I'm going to find a critical number, I'm supposed to set this equal to 0, which means that it really needs to be cleaned up so that the algebra becomes a little more clear. Let's take this 2x and move it to the front. This becomes 1/2 times 2x times x squared plus 25 to the negative 1/2. So what I'm going to do is multiply this 1/2 times a 2. That gives me 1. So I have x times x squared plus 25 to the negative 1/2. The very last thing I'm going to do is put this term down in the denominator and make the power positive. So flip this back down in the bottom since that has a negative power. That becomes x over x squared plus 25 to the positive 1/2. Now this is my derivative function. I'm going to take that now and set it equal to 0 because that's how I'm going to get my critical numbers. When we set this equal to 0, I have a fraction set equal to 0. Now the thing about fractions is the bottom's never allowed to be 0. That's where domain restrictions come from. So if you have a fraction set equal to 0, the only thing that's allowed to happen is that the top is set equal to 0. So the top of this fraction is x, so I set x equal to 0. And that means, because this is just x, that we've now solved for x. X is 0, as it happens. And so this is my critical number. You set the top equal to 0. This time we're setting x equal to 0. So then x is equal to 0, and we're done. There's my critical number. What I'm going to do now, oh, and I do want to point out that my original function was not a fraction, but my derivative function now is a fraction. So when I look at this fraction, you might have to consider whether or not the denominator is ever 0. In this particular case, that answer is no, because this bottom here is added, and I have something that's squared down there. But I might have a domain restriction that comes out from the derivative, because this is a fraction. But anyway, this one doesn't have that, but it can happen. We have a critical number, x equals 0. What am I supposed to do with it? I'm supposed to plug my critical number into the second derivative. That's what makes it the second derivative test. So if you don't already have the second derivative, you need to find it. My original function is up here. It's this one and this one. And I'm supposed to take the derivative of this right here. And if I'm looking at that and I want to take the derivative of that in order to find the second derivative, I'm going to need to use a quotient rule. So now I need to use a quotient rule in order to take the second derivative. Now here's where you might want to be careful. My second derivative is called f double prime. And if you want to, we can use this. I'm going to use a little bit of side scratch paper here. In general, the quotient rule is given by g times f prime minus f times g prime all over the square of g, where you have to let f be the top of the fraction and g be the bottom. So what I like to do is come over here and make a list, and I label my parts. For this quotient, the top part, x, is labeled as f, and the bottom part of my fraction is labeled as g. So that would be x squared plus 25 to the 1/2 power is g. We then have to find f prime and g prime in order to complete the list of things I need to use a quotient rule. If f is x, then f prime is the derivative of x, which is 1. If I'm going to do the derivative of this, I'm going to need to use a general power rule because this is something in parentheses to a power now. So let's do a general power rule on this. C times r, 1 times 1/2 is 1/2. Leave the inside alone. Decrease the power by 1. 1/2 minus 1 is negative 1/2. And then you have to multiply by the derivative of the inside. The derivative of x squared plus 25 is 2x. When you multiply 1/2 times the 2, you get 1. Then you have x times x squared plus 25 to the negative 1/2. Looks a little bit familiar. This is my f prime, g, and g prime. Take all of these, drag and drop, put them into the quotient rule formula. g times f prime minus f times g prime all over the square of g. I'm going to write this up here. G, which is x squared plus 25 to the 1/2, times f prime, which is 1, minus f times g prime, all divided by g squared. So g is x squared plus 25 to the 1/2. And I'm supposed to square that. So I get here. Now this is my second derivative, and I'm supposed to be plugging my critical number into the second derivative, ultimately, right? We're supposed to find the second derivative, and as part of the second derivative test, I'm supposed to take this critical number and plug it in. So this is where I'm going to ignore the fact that this is really ugly, and I'm going to go ahead and plug in x equals 0. Nice things start happening there. You'll have 0 plus 25 to the 1/2. So that means you have 25 to the 1/2 times 1 minus 0 times that, which means this whole term is going to be 0. 0 times 0. And then in the bottom, you'll have 0 plus 25 to the 1/2, which is 25 to the 1/2, and that's being squared. So when you punch this out, you have 25 to the 1/2, which means square root of 25, which is 5. 5 times 1 minus 0 over 25 to the 1/2, which is again square root of 25. 5 squared, which is 25. You get 5 over 25. Now, what does this mean? What that means is that you get a positive result out from the second derivative. Remember, you're doing a second derivative test, and you're supposed to take this critical number and plug it into the second derivative and get a value. The value we get is 5/25, which is a positive number. So we're supposed to draw some conclusions from this. So it looks like I need a little bit more scratch paper here. What are my conclusions going to be? If my function has a positive result, or my second derivative has a positive result, that means that my original function is concave up at that critical number I plugged in, x equals 0. Plug 0 into the second derivative, positive result. Positive result from second derivative means concave upward. So this is the direct consequence of this statement here. F is concave up at x equals 0. But it's up to us to put 2 and 2 together. 0 wasn't just some random test point. 0 was a critical number, and as such, it is potentially a max or a min. So if we're plugging in 0, and my function is concave upward, has an upright bowl shape, then what type of max or min would you get? It would have to be a minimum there. So the conclusion we would make is there has to be a local minimum at x equals 0. So to put this as a final answer, let's find the xy point that corresponds to x equals 0. So x is 0, y is, if you take x equals 0 and plug that back into the original function up here, get your y value. Y values come from the original function. Plug x equals 0 into this, you get square root of 0 plus 25, which is square root of 25, which is 5. So the y value, when you plug 0 into the original function, is 5. What we would say is there's a local minimum at x equals 0, and the local minimum is 5. All right, we have one more to do, and we'll be done with number 2, it looks like. Well, no, number 3. because the next one's number 4. We got part F. My function is 2x plus 18 over x. And so we're getting into a pattern here. What am I doing? I've got to find my critical numbers and plug them into the second derivative. So my first step is to find any critical numbers. And how am I going to do that? You're going to take your derivative, your first derivative, and set it equal to 0. If I'm going to take the derivative of this function, I need to get it in a more derivative appropriate format. Take this x and flip it up. This is 2x plus 18, x to the negative 1. Find the critical numbers by taking the derivative. The derivative of 2x is 2. This part, you have a power rule. 18 times negative 1 is minus 18, x to the negative 2. Now, what am I fixing to do with this? I'm about to take this thing and set it equal to 0. So that means this x to the minus 2, let's flip it and kind of put it back in its standard place in the denominator. Let's take that and set it equal to 0 so I can find my critical numbers. Add the 18 to the other side. I'm going to take this term and move it. I get 2 is equal to 18 over x squared. Multiply both sides by x squared. That way on the right, all I'll have is 18. And over here, I have 2x squared. Divide both sides by 2 here. You get x squared is equal to 9. And then square root both sides. To get x is plus or minus 3. So you have 2 critical numbers here. 2 potential maxes and mins. I have x is equal to 3 and x is equal to negative 3. Those are my critical numbers. That means I have to take them both and plug them into the second derivative. So this is part 2 of this mess. I need to find the second derivative because I'm about to plug those 2 numbers into it. So find your first derivative before you simplified it. It's right here. Take the derivative again. The derivative of 2 is 0. The derivative of negative 18x to the minus 2 is a power rule. Negative 18 times negative 2 is 36. X to the negative 2 minus 1 is negative 3. So my second derivative function, once you make it proper and put this x to the minus 3 back where it goes, is 36 over x cubed. Let's take our 2 critical numbers over here and plug them into the second derivative. This is what makes it the second derivative test. And let's see what I get. If you plug 3 into this, 36 over 3 cubed, that looks like a positive value to me. I'm supposed to draw a conclusion from that. Positive value from the second derivative means what? It means your function's concave up. Let's plug in negative 3. I get 36 over negative 3 cubed. Negative 3 cubed is negative 27. So I have 36 divided by negative 27, which is decidedly a negative number. If you have a negative number, what does that mean? Well, a negative number out from the second derivative means that your function is concave down. So we got up and down, respectively. I'm supposed to draw further conclusions from that. This 3 was no random point. That is a critical number, which means it's potentially a max or a min. But if it's a potential max or a min, and the shape of the graph is concave up, then it must correspond to a min. So we'd say that there's a minimum, a local min, at x equal positive 3. Similarly, at negative 3, it's a potential max or a min, but my shape is concave down. So if it's concave down and potentially a max or a min, which does it have to be? It has to be a maximum. So we have a local max at the negative 3. Tidy this up by finding the points. The local min is at 3, but it'd be nice to have the xy coordinates so you could plot it. Let's find the point corresponding to that. We're going to have 3 comma y and negative 3 comma y. So we take these critical numbers and plug them back into the original function. That's what the original function does, is crank out y values. So when you take positive 3 and plug it in here, you get 2 times 3 plus 18 divided by 3. You get 12. When you plug in negative 3, you get 2 times negative 3 plus 18 over negative 3. You get minus 12. So we have y is positive 12 at x equal 3, and y is negative 12 at negative 3. So the way we would say this is there's a local min at x equal 3, and the local minimum is 12. There is a local maximum at negative 3, and the local maximum is negative 12. All right, let's scooch on to number 4. We'll finally be doing something a little bit different. It says, find the minimum marginal cost of a product if the cost function is given by C in dollars, where X is between 0 and 150. Now let's read into some key terms here. It says, find the minimum. Find the minimum. That means it's looking for a local min. So in this way, it's very similar to what we were just doing. What we were just doing is finding local mins and maxes. At this particular case, it wants a min specifically. That is to say, I can use the same exact process that I've just been doing. How do you find a minimum? You find critical numbers, you plug them into the second derivative, and you see what happens. That'd be the second derivative test. Now, let's pay attention to the wording. It says find the minimum marginal cost. That means you're supposed to find the minimum of marginal cost. So my question to you is, do we have the marginal cost function in front of us? If I scooch up as kind of a comparison, we have this function given to us, we find its critical numbers and find its local maxes and mins. So what's the process? You give me f, take the derivative, set it equal to 0, find the critical numbers, and plug those into the second derivative. Give me f, take the derivative, set it equal to 0. F, take its derivative, set it equal to 0. So we would say that these are local minimums of the function that I originally had. If I want to find the minimum of marginal cost, I need to be starting with the marginal cost function right in my face. Do I have the marginal cost function in front of me? And the answer here is I do not. What do I have in front of me? I have what's called just the cost function, or sometimes they call it the total cost. This is not the marginal cost function. How do I get the marginal cost function? I have to take the derivative of this. So that is to say, I can't start the process of take the derivative, set it equal to 0 to find the critical numbers, because I don't even have my original function yet. I have to build it. So let's find my starting function. And just for the sake of distinguishing it from the cost function, let's call it MC, marginal cost. This is the function I'm trying to find now, marginal cost. So if I'm going to find this marginal cost function, how do you get marginal cost? You get marginal cost by taking the derivative of total cost. So once I take the derivative of that, I'm going to have my starting function. So let's take the derivative. I'm going to have a power rule here, 0.0001 times 3 is 0.0003 x to the 3 minus 1 power minus 0.036 times 2, I have another power rule, is negative 0.072 x to the 2 minus 1. The derivative of 16.8x is 16.8 because the derivative of x is 1 and the derivative of 1900 is 0. So this is my marginal cost function, which means we're here now. We have our primary function. Now that I have my primary function, how do I find its minimum? Well, this is where we need to take the derivative, set it equal to 0, and solve for x. So take this thing, take its derivative, set it equal to 0, solve for x. I want to find its critical numbers. So here's my marginal cost function. I'm going to take its derivative, mc prime, and I get, this is another power rule since I have x squared, 0.0003 times 2 is 0.0006, x to the 2 minus 1, or x to the 1. The derivative of 0.072x is 0.072, and the derivative of 16.8 is 0. So you take this, and I'm supposed to set this equal to 0 and solve for x. This gives me a critical number. I'm going to take this 0.072 and add it to the other side. Divide both sides by 0.0006. Don't drop a 0. And we get x is 0.072 divided by 0.0006. And you get x is 120. This is my critical number. This means this is my potential maximum or minimum of the marginal cost function. So this is my primary function. So this is the potential max or min of that. How am I going to verify that it's a max or a min? Well, I'm going to do step 2 of this process, which was what? Plug the critical number into the second derivative. So let's find MC double prime. Take the derivative of this again. The derivative of 0.0006x is 0.0006. The derivative of 0.072 is 0. So this is my second derivative. And this is MC double prime of x. But what we have here is that this is a number. This is constant. So it doesn't matter what I plug in for x, I'm always going to have this number. That is to say that if I, quote, plug in 120, there's nowhere for me to plug the 120 into. There's no x here. So I'm always going to get 0.0006. But I'm supposed to draw conclusions from this anyway. I have that the second derivative is a positive number. What does this tell you about the function? This tells you your function is concave up. So if it's concave up at this potential max or min, which does it have to be? If it's concave up, that shape dictates that x equal 1 must correspond to a local minimum. Okay, so x equal 120 corresponds to the local min. I then have to kind of check and make sure that we answered the question. We found the x value that corresponds to a minimum of that, and we verified that it does correspond to a min. Now, did it ask for the x value of the local min, or did they ask for something else? It said find the minimum marginal cost. Since it's asking for the marginal cost itself, that means it's wanting the corresponding, quote, y value of this x. So this x is how many items it would take to manufacture to get this minimum. But I need to take this and plug it back into the marginal cost function to actually get what that cost is. So I'm going to plug x equal 120 into the marginal cost function, which is up here. If you plug x equal 120 into this right here, and punch it out, you get MC of 120 is, plug it in up here, 0.0003, 120 squared, minus 0.072 times 120, plus 16.8. So let's punch this out on our calculator, being very careful here. 0.0003 times 120 squared minus 0.072 times 120. And let me put parentheses around this just because I'm paranoid. There we go. Plus 16.8. We get 12.48. So the minimum marginal cost is $12.48. So this is the answer. We know that 120 items corresponds to the min, but the actual minimum cost is 12.48. So that's the answer to problem 4. So be cautious with this one. It said find the minimum marginal cost, but they didn't give me the marginal cost function, so I had to build it. How do you get the marginal cost function? You take the derivative. So what we did, we took this cost function, take the derivative, and this is your starting point. This is your ground zero. This is your marginal cost function, so then you have to find the critical numbers of it. Take its derivative, set it equal to 0, blah, 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 blah. But this is your starting point. You have to manufacture the function because they didn't give it to you. And you have to manufacture it by taking the derivative of C. All right, we can now scooch on to the last problem, which is quite a bit different from the ones we've been doing. To do this one, I'm going to need a definition. So for that, I'm going to go back to the definition pages, beginning of the section, the second page. We look here, I haven't quite talked about this yet, but we're going to need these here to do this last problem. It says the point at which sales, so you're selling something, the point at which your sales continue to increase but start to slow down, this is called the point of diminishing returns. So your sales are still going up, but they're starting to slope downward. We're not selling as much. So when that happens, it's called the point of diminishing returns. And mathematically, the point of diminishing returns occurs at a point of inflection, an inflection point, which is something that you learned about in the last section, 4.1. An inflection point is a change in concavity, but a point of diminishing returns particularly occurs when your curve changes from concave up to concave down, specifically in that order. It starts out concave up and then it moves to concave down. If that's the case, then that's a point of diminishing returns. So if I'm going to flip back here to this last problem and reread it, it says the sales function of a product is given in S, where X represents thousands of dollars spent on advertising, and X is between 0 and 12. So that means 0 and 12,000. S is in sales in thousands. Find the point of diminishing returns. So when it says find the point of diminishing returns, that means that I'm finding an inflection point, particularly an inflection point where it starts out as concave up and moves to concave down. If I'm going to find an inflection point, remember from the last section, if I'm going to find an inflection point, we need to do a number line analysis and figure out where the graph changes concavity. So in this problem, I'm going to need to do a number line analysis using the second derivative, because the second derivative does concavity. This is similar to the number line analysis that we did in chapter 3, and you would have done this in the last section. If I'm going to do a number line analysis, I need my potential inflection points. Those are called hypercritical numbers. So what we're going to do here is find any hypercritical numbers. Those are my potential inflection points. Just like critical numbers are potential maxes and mins, hypercritical numbers are potential inflection points. And you get hypercritical numbers by setting not the first derivative, but the second derivative equal to 0 and solving. So we have an outline of what we're going to do. What I'm going to do is find hypercritical numbers of this function by taking the second derivative and setting it equal to 0. And then I'm going to do a number line analysis and show that the concavity changes. So let's make a couple of notes here before I get started. It says X is in thousands of dollars. So that means if X is 1, for example, that's 1,000. And sales is also in thousands. So if I get an answer of S equals 8, for example, that would be 8,000. And I will have to transfer that over into thousands in order to answer the question. So let's keep that in mind. All right, let's get to it. I've got to set my second derivative equal to 0. In this case, my function is called S, so that means I'm going to find S double prime and set that equal to 0. So let's get started. I first need to find the first derivative of sales. Derivative of 204 is 0. Derivative of 6.3x squared, 6.3 times 2 is 12.6. X to the 2 minus 1 minus 0.25 times 3. I have yet another power rule there. X to the 3 minus 1. This is my first derivative. I now have to take the second derivative because I want hypercritical numbers. Those come from the second derivative. Let's find the second derivative. The derivative of 12.6x is 12.6. The derivative of 0.75x squared, I use a power rule there, is minus 0.75 times 2, which is 1.5, x to the 2 minus 1. You take your second derivative and you set the second derivative equal to 0 to get your hypercritical values. Those are my potential inflection points. So let's solve this. Add the 1.5 to the other side. Divide both sides by 1.5. I get x is 12.6 divided by 1.5. Which is 8.4. So this is my hypercritical value, which means this is a potential inflection point. I have to show that it is an inflection point, which means I have to show that the concavity changes. So this is where I'm going to recall something that I did in the last section. I would have made a number line here, and on this number line, I would put x equal 8.4. Now I have to be cautious here because this is not an infinite number line. They said x is boxed between 0 and 12. So instead of having the left side's minus infinity and the right side's infinity, I would have 0 and 12 here because it doesn't go off to infinity. X is boxed in between 0 and 12. 8.4 goes on my number line. This is my neutral zone for concavity. And what you have to do is pick test points in this region between 0 and 8.4, and then between 8.4 and 12, and you're going to plug test points into the second derivative. So let's say that I picked a test point x equal 2 in between 0 and 8.4. And let's say that I chose x equal 10 between 8.4 and 12. What I'm going to do is plug those into my second derivative, which is right here, and see what happens. Interpret my results. So I have 12.6 minus 1.5 x. And I'm going to plug in my two test points. I'm going to plug in x equal 2. And this tells me that my second derivative value, when I plug in 2, is 9.6. When I plug in 10, my second derivative value is negative 2.4. Now I have to translate those. These two values are just test points. But what they do is tell me that I get a positive result when I plug in 2 in the second derivative. Positive result from the second derivative means concave up. So I know on this region here, between 0 and 8.4, my graph is concave upward. Similarly, I took x equal 10 and plugged it in here, and I got a negative result. This means, since this is a negative result from the second derivative, that my function is concave down at x equal 10, which means that it's concave down on this whole region here. So we've shown that the concavity changes. It goes from concave upward to concave downward. And therefore, since 8.4 was my potential inflection point, we have now confirmed that it is, in fact, an inflection point because the concavity switches. Is it a point of diminishing returns, though? In order for it to be a point of diminishing returns, it has to specifically go from concave upward to concave downward. And we do see that that happens. I start out at concave upward here, and then it switches to concave down. So what we should conclude is x equal 8.4 corresponds to a point of diminishing returns. So let's zoom out and go back up here to the question and see what it's asking for. Does it want an x value or does it want something else? Since it says to find the point of diminishing returns, we're going to treat this as if it wants an xy point, like an actual xy point. I have x is 8.4. I need the corresponding, quote, y value, but that's really just s. Right now, our sales is our function. So if I'm going to find the point, I need to plug 8.4 back into the sales function all the way up here. Now, if you take 8.4 and plug it into your original function, s, up here, you get 500.35. So I take x equal 8.4 and plug it in here. You get a value of 500.35. And this is your sales. But the thing is, if you remember, 8.4 is in thousands, and so is this. So I have to multiply these both by 1,000 to get my true point. My point is, take 8.4, multiply it by 1,000. 8.4 times 1,000 is 8,400. And when you plugged 8.4 in, you got 500.35. So take 500.35 and multiply that by 1,000, and your sales is $500,350. So this point, X represents thousands of dollars spent on advertising. So they spent $8,400 on advertising, and that got them a total sales of $500,350. So this is the point that you would have to enter into your homework. Make sure to convert it into thousands. Okay, so we are done with this section. We finished section 4.2, talking about the second derivative test. See you next time.